In this part 5 of my unit on comparing and contrasting linear and exponential functions, we continue focusing on linear functions, and we're going to do a proof in this video of a general principle that we've observed in a couple examples in the last couple videos for describing how linear functions change. We also want to visualize this fact, this principle, geometrically using similar triangles. I'm working in Mathematica, this computer program that you see here, and we're going to visualize what we want to describe with a couple new Mathematica commands called graphics and line. So here is the first example, modeling the population of Austin, Texas, and we're making the simplest assumption we can that the function is linear. Here was the function we used to model that population from 2010 to 2013. And this was the general principle that we've been focused on here recently. The change in the population, delta P, is ultimately proportional to the change in the time. In this case, 31.7 thousand people per year times the change in time in years. For example, if the time changes by 2 years, you'd multiply 31.7 thousand people per year times 2 years to get a change of 63.4 thousand people as your approximate change in P. It's proportional to the change in T if we assume it's a linear function. Here is our second example, car depreciation. We are again assuming the simplest kind of model here, a linear function. V is the value of the car as a function of time in years since 2013. And we came up with this equation, V equals 24 minus 3t, to model that depreciation in value. And we again saw this principle here that the change in the value, delta V, is proportional to the change in time. Negative 3 times the change in time. Negative 3 is again the slope, just like 31.7 was the slope in the previous example. Here this is negative $3,000 per year. This leads us to make a conjecture of a general principle. Here's our general principle. If f is a linear function, then delta y is proportional to delta x. That's our main fact. You might call that a theorem. General facts, abstract facts in mathematics are often called theorems, but I'm calling it a general principle here. It's an if-then statement, and we want to prove it using logical deduction. We want to assume we've got a linear function and say we even have this particular formula for it. That's what it means for f to be linear in this context. And we want to assume that x is changing by a certain amount, delta x, and show delta y is proportional to delta x. Specifically that this equation is true, and even more specifically, m, the slope, is the constant of proportionality, and that in fact is the reason we say that the slope is synonymous with the phrase rate of change. Okay? Proofs should be written in sentences. They are logical arguments, so I will strive to write my proof in a sentence form here. So I'm going to start by saying, suppose f is a linear function. Essentially, I'm going to rewrite my first sentence here, or the first part of the first sentence. Say f of x equals mx plus b. That's what it means for f to be linear in our context. Actually, if you take linear algebra, it means something different, but I won't get into that. I don't have to have a dependent variable here, but it's nice to specify a dependent variable. Call it y. I'll go ahead and put a y equals f of x equals mx plus b there. And suppose the independent variable, which I'm calling x in the formula, changes from a value of, okay, now I'm going to use the same letter x, but here I'm thinking of x as being something specific. Imagine a number line, draw a point in that number line, label it with the letter x, to a new value, well, x plus delta x, so it's changing by delta x. Okay? This language of change is not real precise, all right? That's okay. It's very suggestive visually of what you want to imagine. You draw a number line, you mark a point x off, and you imagine x changing by an amount delta x. If delta x is positive, it moves to the right. If delta x is negative, it moves to the left. What happens to y? Then, essentially by definition, the change in y, delta y, is the new value of the function at the new input, x plus delta x, minus the old value of the function at the old input, f of x. But what does that equal? All right, now you have to use the formula. f of x equals mx plus b. When you plug in x plus delta x, I've talked about this before, you need to replace this x here with x plus delta x. So you get m times x plus delta x. Realize conceptually that this is f of x plus delta x. This is m times x plus delta x. You need to realize what's going on here. So in the second expression, we're going to be able to use the distributive property. Don't forget to add the b. Then subtract f of x. Replace x with x. You're subtracting the whole thing, so we want to use parentheses there as well. Now use the distributive property. We get m times x plus m times delta x plus b. Distribute the minus sign through this set of parentheses here, minus m times x minus b. Then we get cancellation, just like we've seen with particular examples. The mx's cancel and the b's cancel, leaving us just with m times delta x. Okay, that is essentially it. This proves that delta y is proportional to delta x for a linear function. When mathematicians finish proofs, they often get quite excited and start talking in Latin, and they write things like QED, which is a Latin abbreviation for Quod Erat Demonstrandum. I'm not sure if I pronounced that right. It means I'm done, essentially. I proved what I wanted to prove. All right, fairly simple proof, but you need to realize what you must do for the proof. That's kind of the hardest part of it. What we want to do now in the last few minutes of the video is we want to illustrate what's going on here with Mathematica. Let's go back up here. What I'd like to do is I'd like to add some lines to this picture here. We talked about using the show command in the last video to combine plots, to combine graphic objects. This command right here, this plotting command, essentially created the red line. Plot of points was another plot that I combined with the other plot, the red line, with show, separated by a comma here. And plot of points was a variable in which I had stored a graph, this particular graph. And so by putting both of these things within a show, I could combine the graphs. I get the red line and the black dots. You can combine more than two graphic objects. You can combine 3, 4, 5, etc. I'd like to use two new commands, graphics and line. Essentially, the line is going to go inside the graphics, actually, to create some line segments to illustrate the general principle that I'm talking about here. I can do it within the show, say between the plot and the plot of points, or I could put it after the plot of points as well. Graphics is the basic command, okay, and within graphics, I'm going to put some input. I use the square brackets there for the input of graphics, and I'm going to use curly braces here to put some other stuff. I'm going to use an option thick and a color blue, and I'm going to create a line. Okay, take a look at the syntax. This is the basic syntax that's going to create a thick blue line between a couple points. I now need to specify what those points are. Inside line, I put curly braces again, and inside those curly braces, I'm going to put 2 points. The first line I'm going to create is going to go from this point, 0, 790, over to this point under this one, 10, 790. This is t equals 10 there. I type 0, 790, and that point, put a comma, then type 0, 10, 790. And I'm going to see a thick blue line like I just described. There we go. I just entered it. Now I'm going to take another line. I'm going to create, starting at this point and going up to this point. I can continue within the same line code here. I can put 10, comma, the second coordinate of this point up here, I believe, was 1107, if I recall correctly. Yes, that looks right. So there we have a couple lines connecting these points in this way. This is a perpendicular angle here, a 90-degree angle, creating a right triangle. All right. The ratio of this side to this side is rise over run. It is the slope, which was 31.7 thousand people per year in this context. If I pick two other points, let me copy and paste this code and change the points that I picked. Let's say I picked 2, comma, whatever f of 2 was. I'll type in f of 2. Over to 8, comma, f of 2. And then up to 8, comma, f of 8. What line I'm going to create. Remember, f is the function. 2 comma f of 2 is this point. 8 comma f of 2 would be this point over here where t is 8, and the second coordinate is f of 2, and 8 comma f of 8 would be this point here. So I'm going to create another right triangle looking like this. There it is. These two right triangles are similar to each other, okay? They have the same shape, the same angles, different lengths to the sides, but the same angles. Because they are similar triangle, the ratio of corresponding sides is the same. Rise over run in both cases is the same number, and in both cases is the slope m, in this case 31.7 thousand people per year. That is a visual geometric reason or illustration of my general principle here, that you get the same, well, that m is that constant of proportionality. In fact, of course, if you take this equation and solve it for m by dividing both sides by delta x, you get the definition of slope. You get m equals delta y divided by delta x. You get rise over run. And it doesn't matter what 2 points you pick. And with that, I'll end this video.